In that case, the floor is all yours.
Okay, well, thank you. Thanks for the invitation to come talk today. A little bit of context, the work that I'm going to talk about is coming from, there's a big center in the Department of Energy in the US. It's called a MIMIC center called FILMS. It's PI'd by George Karniadakis that I'm a part of, which is basically developing scientific machine learning. It's a few years into that, and I'll also be talking about work from my Department of Energy early career program, which is really targeting blending mimetic PDE discretization with scientific machine learning architectures and so on. So to start, I'd like to contrast scientific machine learning against traditional machine learning. So we're really in like a very different kind of space. So traditional machine learning, there's all these tasks: classification, image processing, NLP, and so on. Each one of these basically has a custom tailored architecture, which is the secret to success in each one of these applications. And so for each one of these kind of applications, it's slightly different from scientific computing, where it's a lot more about qualitative comparisons, rankings, classification, and so on. And in these cases, accuracy is actually kind of bad, right? What you'd like is, oftentimes improved accuracy translates into overfitting and poor generalization. And so, historically, people just aren't really all that concerned with the kind of things that tend to interest us in the scientific computing world. So for us, things look pretty different. One, data is much more irregular. We have to handle, right? We don't have like Cartesian grids of pixels like you would in an image. And instead, we have complex CAD geometries, multiphysics, multi-scale, all the usual kind of things. And also, unlike like Google or Facebook, we're working in a very small data regime in a certain sense. So, we don't collect like billions of people's Facebook profiles. We have, typically in Department of Energy, we have very costly experiments from our user facilities. So this is a picture of the pulse power fusion device that we work with. I'll talk a little bit more about this later. But typically we can only do a handful of experiments. Now, each one of those experiments may have an absolute massive amount of data associated with it, but we can only afford small realizations of a given experiment. Right, and so typically we care about doing things like learning constitutive models, fitting PDE-based physics models to build data-driven models, dynamical systems, doing UQ and so on. And so the usual tools for this is very mature approximation theory, finite element spaces, and so on. Variational principles, things like Galerkin methods that let you prove things about stability. And then this more modern takes on numerical analysis are really focusing on preserving geometric or algebraic structure and mimicking properties of the continuum equations. So basically what we'd like to do is we'd like to develop our own set of customized architectures that'll give us scientific machine learning tools with the kind of guarantees that are just an absolute necessity for the kind of work that we do. So historically, if you look back over the last maybe 5 or 6 years, this explosion of machine learning and scientific computing, maybe like 5 or 6 years ago, there was a big push where people would take their DNS codes, their massive simulations and so on, and stuff them into TensorFlow, and they would have these kind of outrageous claims, right? That you could, you could solve a PDE like 100,000 times faster or something like that, right? But if you actually use this in a scientific computing context, because it's, these black box off the shelf computer science machine learning architectures, there are no guarantees regarding stability or anything like that. So as soon as you start trying to make predictions and do more than just interpolate between existing solutions, your things blow up. So the last maybe 3 years or 4 years, physics-informed machine learning has emerged as a popular technique to alleviate these kind of big data requirements. So the idea is, you have your data, you add a regularizer in order to impose some sort of inductive bias on a physics prior, right? So for example, if you're trying to learn a model for a fluid flow, a fluid dynamics system, right? You might assume that those satisfy the Navier-Stokes equations and penalize their deviation from that. The problem with this, though, is that one, you have this kind of empirical hyperparameter that you're using to penalize. It's not clear how to choose that. As you go to complex systems, you might actually have a dozen of these hyperparameters. Who knows how to pick each one of those? And then also, these physics are only imposed to within optimization error. So very few people do this, but if you go in and you plot this residual, right, and see how tightly it's actually satisfied, oftentimes, maybe 1%. Right. So for some applications, that's perfectly fine. And this is extremely simple to code up, so that's why it's popular. But particularly for things like the high consequence engineering decisions and design problems that we're concerned about, you need much more stringent requirements than that. So the idea for all of this work is that we're basically going to engineer those physics directly into the neural network architecture, same way that you would design a finite element space, for example, right? Finite volumes are naturally conservative. You don't have to penalize conservation or anything like that, right? And the hope is that this will give us these kind of guarantees: accuracy, stability, and physical realizability, particularly in small data limits, right? So even if you only have one data point, you'll have all these guarantees associated with the model that you've put together. This is also relevant for uncertainty quantification, optimal design, and so on. So you can imagine a parameterized PDE, right? So you have some parameter theta and a family of solutions that are parameterized by theta, right? So for example, in this thing, you could have a number of different diffusion coefficients for this unsteady diffusion equation, but this could really be anything, porosity for subsurface flow, material properties, chemistry, blah, 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 whatever you want. And so the tools that I'm going to discuss today map onto this problem as well. So basically, we're able to show that they break the cursive dimensionality. And we're able to enforce these kind of physics constraints tightly. So this is, to give a sense of where our targets are, this is where we're moving toward right now. So the outline for today, like I said, is we'd like to figure out how to engineer traditional modeling and simulation requirements into these deep learning architectures. And there's two thrusts. I'm going to consider accuracy, right? You would like it to work the same way as finite elements, right? You want to do some version of mesh refinement. And what that means in this context is, as you go to a wider or a deeper network, right, you'd like a guarantee that that you're getting some convergence to whatever the underlying thing is that you'd like to approximate. The second thrust is structure preservation and stability. This is where all this kind of mimetic, structure preserving, all these ideas come in. And to start, I'm going to give a couple of motivating applications. Just, I don't know many of you, so this will be particularly helpful for understanding why structure preservation is so important to us. And the key thing for all of this is, there's two things. One, for these kind of things that we're developing, we really need guarantees, right? We need to know, like, it's perfectly fine to have a postdoc go and play with TensorFlow and tune all the knobs, and all of a sudden you have like a very nice picture which you can publish in a journal. But in order to fold these into these kind of high consequence simulation pipelines, you really need guarantees that your model isn't going to blow up, that that it's behaving in a desirable way. And the other factor is that these kind of data-driven models that we're going to put together live in an ecosystem of production code. All right, so for example, Sandia manages, we're involved in the Earth, the E3SM project, which is the big climate model for the entire planet. That's built up of submodels like atmosphere, ocean, land ice, sea ice, so on. Each one of those submodels has a separate model, right? So within atmosphere, there are cloud models, which are a candidate for data-driven models. So if you're going to try and machine learn a cloud model, for example, you need to guarantee that when you hook that into all of these other kind of legacy codes that it's not going to break everything. It has to fold in nicely, satisfy interface conditions, and so on. So one problem that we're interested in is semiconductor design, right? And so we'd like to build like circuit level system designs, and imagine like a circuit board that's going to go into a satellite and go up into space. And the challenge with that is these things that go up into space get bombarded by solar radiation, and that alters the fundamental model, the physics that are going on. So you need some way of being able to assimilate the effects of this radiation damage. And so typically what we have are these what are called TCAD models. They're drift diffusion equations, finite elements. And so for a single semiconductor, like one transistor, you can simulate this with millions of elements, for example. But of course, the system scale design has many of these, millions of these things, right? So there's a multi-scale problem. And typically what people do is they have these, they construct empirically these circuit models, which are meant to replicate the IV curves, kind of the Dirichlet de Neumann map associated with this PDE model, but they're cooked up totally arbitrarily. So over the course of a decade, someone kind of squints and they say, oh, what if we had a loop here, a capacitor here, and so on. And eventually they get a good surrogate for each one. But of course, if this thing's getting hit with radiation, you can't land your satellite, take another decade and recalibrate your model, right? So what we're after is a means of doing some online data assimilation, right? So that we can automatically generate these kind of network models, which have a lot of desirable physics built into them. And so what we might do is you might take this, this PDE model, you use that to generate a high fidelity data set. There's a lot of interesting work that we're doing related to topological data analysis and partitioning, right? So basically you want to break this into some representative control volume subdomains that capture the relevant physics. And then once you have this partitioning of space, that induces a graph, right? You have nodes for each subdomain and an edge for their shared interfaces. And so we call this graph a model backbone. And then what we'd like to do is attach a model to this model backbone, right? And the hope is that we can train this model in such a way that it inherits the fidelity of this high fidelity simulation. And so it's something sort of like reduced order modeling, but it's not the usual thing where you do PCA and then put it through a least squares residual minimization, right? It's not a variational construction. This is really a data-driven control volume kind of analysis, and you get a lot of structure preservation as a result of that. The second problem that we're interested in at the lab is we have this big pulse power fusion facility called the Z machine. And so this isn't something for generating power. This is an experimental device. So it generates a fusion environment for a very short period of time for doing foundational science. And this is a user facility. So you can write a grant and get time on this machine the same way you would on a supercomputer in the rest of the DOE labs. And so the way this thing works is you have this is like the size of an ice hockey rink. Around the perimeter of the room, you have 1 to 2 story high capacitors. That's what these black boxes are. And so these just get pumped full of electricity. And then when it's time for the experiment, you discharge all of these capacitors, and they all arrive at a tiny box, less than a cubic foot at the center of the thing, right? So that generates an extreme environment that you can use for all sorts of foundational science. But basically, it's a way of generating intense electromagnetic waves and radiation. And so one kind of foundational science thing that we do is what are called flyer plate experiments. You take a flyer plate, and this is just, think about this as just like a ballistic object, and you're using these massive electromagnetic waves to accelerate this flyer plate. The same kind of thing you might do with a rail gun or a pneumatic gun or whatever. So you launch these things into a material under test, and then that causes a shock to propagate through this material. And this is a means of generating Riemann problems in extreme environments that you can use to understand shock dynamics. People call them shock hydrodynamics in these kind of extreme settings, right? So the kind of thing that we'll do, right, is we'll do this experiment. We'll get profiles of the usual density, momentum, energy, the kind of things that the Euler equations describe. And the job is to discover a equation of state which can be used, which is consistent with these measurements, right? And so for this, there's a lot of, so once you've learned an equation of state, you can break it off, you can plug it into a production code, and then you can use that to simulate much more complicated scenarios. And so this is a recent paper where we talked through this. There's a lot of very interesting physics-informed physics constraints you have to get right, like entropy and so on. The thing I'm going to talk about now, so these are really the things we'd like to do, right? You've probably seen this before if you've done anything with machine learning. If you have tons and tons of data, as you increase the width or the depth, if you look at the error rate, if you're just regressing like sine 2 pi x on the unit interval, what you'll see is it converges very quickly, but then it stagnates, right? So these things are great for getting 1% error, especially in high dimensions, because they break the curse of dimensionality in a certain sense, right? But they don't give us the kind of HP convergence that we're used to from the finite element world. So there's this one issue that we'd like to fix. The second issue is about stability and convergence. And so really what we'd like to do, going back to pins, which I alluded to before, what we'd like to do is remove these penalty parameters. And for both of these things, we'd like to do this in a way which preserves this scalability of deep learning for high dimensional problems. So this first part that I'm going to talk about is this accuracy piece. And so if we're scientific computing people, when we got started with scientific machine learning, we just want to understand what is a neural network, how does it actually function, right? And so we have this, we have a kind of a series of papers from the last year that dug into this. And so usually there's all this folklore about universal approximation theorems and so on. Those only talk about what's going on in infinite limits, right? So for us, people who care about convergence rates and the like, this is really just like a very small first step, right? Polynomials also have a universal approximation property. No one's freaking out about polynomial approximation right now. So there's all these nice papers. If you haven't seen them, I recommend them, right? But if you haven't seen this, basically a way to understand how they work is that for a multi-layer perceptron, you typically have hidden layers followed by a linear layer. You can call the weights and biases chi h for the hidden layer, the weights for the linear layer chi l, right? And so basically what this thing is constructing is a data-driven nonlinear basis, not unlike what you would get out of PCA. So the output of the hidden layer, all these neurons, you can interpret this as constructing shape functions, right, which are parameterized by chi h. And then you're taking an optimal choice of linear layer weights to best represent your data in terms of that basis, right? So if you look, this is a plot, we're regressing sine x, sine y. And these red dashed lines are the hyperplanes corresponding to ReLU activations. You can see that over the course of training, it's discovering this basis. So in a certain sense, if you're familiar with R adaptivity, that's all neural networks are doing. So we try and think about these things in terms of finite elements because that's our background. And so the punchline, like I said, we have these kind of series of papers that you might take a look at if you're interested. The punchline is what we want to do is break through this optimization error barrier, right? And what people say that, there are all these nice proofs that there exists a neural network which converges exponentially with respect to width and depth and so on, but no one can realize it in practice because you get stuck in suboptimal local minimizers and so on. So what I'm about to show, the punchlines coming first, is that we've figured out a way to break through this barrier and realize the kind of algebraic convergence rates that you're used to in the finite element world. Okay, and the idea came from reading this paper from Christoph Schwab's group, and it's a really, really excellent paper. So I highly recommend it if you haven't seen it. So the idea behind the paper is they show that deep neural networks can emulate a broad class of well understood approximations like finite elements, splines, global spectral approximation, RBFs. And so the idea behind this is, at least for the HP finite element portion of the paper, is that there exists a neural network. Who knows if you can realize it during training, but there exists a neural network where with sufficient depth, you can emulate a partition of space, right? You can build up a partition of unity. And then with an even deeper network, you can emulate monomials arbitrarily well on each partition. And then together, now you have the means for localized polynomial approximation. And that's how you get to HP convergence. So basically what we've done is we've taken this and we've tried to use this as, we've tried to build up an architecture motivated by this approximation theory. And so this is kind of, just some background if you're not familiar with the partition of unity. It's a collection of functions. Each one is positive. They all sum to 1, right? And so we're used to seeing a partition of unity, perhaps, that looks like indicator functions on a mesh, right? So if you have a domain, you partition it into disjoint cells, and then you choose the indicator functions on each cell as one of your partition functions, right? Then that's an example of a partition of unity, right? And in this case, if you do localized polynomial approximation, right, you attach a polynomial space to each one of these partitions, you're left with a DG polynomial space, a broken polynomial space, for example. But there's nothing that says that these partitions have to look this way. This is just the way we're used to doing things in the finite element world. There's this well-established process where you build a mesh, you build a finite element space, and so on, right? But this partition can look like anything. It can look much more complex. You can have partitions that kind of that have overlapping support that kind of bleed into each other, and so on. And you can also do localized approximation in this setting. And so the idea is, what we'd like to do is have a network which, rather than emulate this partition of space and monomials, instead we're going to directly build them into the architecture, right? And so the idea with this is we have this first piece of the network, which parameterizes a partition of unity. And so it's any sort of hidden layer that you'd like. In the paper, we have MLPs and RBF nets. You could have an autoencoder, you could have a convolutional network. And we feed that into a softmax. And this is a standard trick for parameterizing probability distributions. But a probability distribution is a partition of unity. It's a set of positive functions that sum to 1. So we're kind of repurposing this kind of classical thing. And so now that you've got this, and the way to think about this is that this is exactly what classification networks are good at, right? Like partitioning space into that chunk is cats, that chunk is dogs, and so on. So we're kind of isolating that, and that's where we're using the black box machine learning. But now on each partition, what we're going to do is we're just going to attach an arbitrary function space, right? To make it concrete, you can think about polynomials, right? So we have a vector of polynomials with an unknown vector of polynomial coefficients attached to each one of these partitions. And the thing that's really amazing about this is that if you're trying to minimize, for example, a root mean square loss with this architecture, and if you freeze the weights in the hidden layer, the weights and the biases, right? So you're only optimizing with respect to these coefficients, you get a closed form solution for the globally optimal polynomial coefficient. So you get a weighted least squares problem. You just need to solve a linear system in order to get this globally optimal representation of your data. So basically what you can do is you can pop back and forth. You can find the best representation of your data given your current set of partitions, and then you can come back and do a step of gradient descent. And this is basically like it's not unlike adaptive finite element methods, but this is, in a certain sense, mesh free, right? You're getting this partitioning of space, but you're not working with geometric objects. And this is all just being done through optimization in kind of a black box way. So I have a little video here which shows how this works out. Say you want to regress this red dashed line, it's piecewise quadratic. This blue line is your current approximation to it. And each frame of this animation is one step of training. And on the left, what I have here is a set of partitions, right? The output neurons of this partition of unity block in the architecture I showed before. And to start with, they're randomly initialized, right? So there's nothing interesting going on. But now over the course of training, what you see is, the partitions trying to help approximate, and then all of a sudden there's this phase transition and it snaps into indicator functions, right? And it's exactly what what any of us would have done if we had to build an approximation for this ourselves, right? We know that because this is only C0 continuous, the only way you're going to get a good approximation to it is if you manually go in and you build boundary, you get cells with interfaces conforming to these discontinuities in the derivatives, right? And so this is able to discover that all on its own. There are a lot of details about the kind of tests. We've done this keeping the number of partitions equal to the number of discontinuous subregions in here and trying to scale it up. And basically what you can see is even as you go to very large, 32 partitions, you're able to preserve less than 1% error. And in some cases, not often, but sometime maybe 1 out of 10 times, depending on how it's initialized, we actually get machine precision representation of these functions. We have an error estimate for this. It's aspirational because, well, I'll explain the error estimate and then I'll say why it's aspirational. So basically, if you have the support of your partitions here, you can derive an error estimate that looks like this. So basically, if the support of the partitions are compactly supported, right, then you can view this as sort of like H, and like a finite element H. It's like the diameter of the element, right? Then you get H to the m plus 1 convergence, where m is an mth order polynomial space, if that's the approximation space you're using, right? So if you can come up with compactly supported partitions, right, then you have HP convergence. So there's a lot of questions about how to actually do training so that you do end up with compactly supported partitions. It's tied to how this works in high dimensions, right? Like if you're working in a high dimensional space with a low latent dimension, there's all these kind of technical things, but the details are in this paper down here if you're interested. So these were those plots that I was showing before. This is basically, we have this kind of toy manifold. You look at data sampled from the X and the Y axis of R2. And you're sampling a smooth function. And in this case, we're using an RBF network, which is it's a single layer network. It's very shallow. And basically what we get is just with width 1, with 2, 4, 8, 16, you're already getting down to 10 to the minus 10 accuracy, where you start to hit some numerical complications with round off error. Really kind of standard for least squares problems. And if you compare that to standard finite elements, right, you might get 1% error, and that's after maybe you're at a width of 16, right? So that's the story for how these POU nets work for smooth data and for discontinuous data. This is kind of a toy thing, but we actually have some recent work that extending this to non-trivial problems, but pedagogically, this gives a picture. If you imagine that your data lives on a latent low dimensional manifold, right? So for example, think about a circle embedded in R2. You know there's a latent low dimensional coordinate. In this case, it's theta and polar coordinates, right? And so what you can try and do is use an autoencoder to learn local coordinates, right? In this case, this x hat is meant to discover this coordinate theta, right? And then you feed that into your partition of unity network, right? So then what this is doing is it's building in a purely mesh-free way a partition of this manifold, and now you've constructed a HP finite element space on a manifold in this black box mesh-free way, right? So if you've ever done any sort of surface PDE, it can be very painful in the finite element setting, right? You have to do things with splines and isogeometric analysis, and so I mean, there's all sorts of ways to approach it, right? But typically, just representing this manifold is a very difficult thing. Then achieving high order convergence is a second difficult thing, right? All of this is kind of popping out of this pipeline. I keep forgetting to fix this movie. It's broken. But this shows basically on this manifold, if you're trying to approximate this, this theta function, if you're trying to approximate this tanh, basically what you can see, this picture on the left during training, each one of these contours shows the support of one of the partitions, right? So your POU is partitioning within the local coordinates, right? But then you can pull that back to the ambient space. And so you can see exactly how the POU is partitioning the entire space, but in terms of this latent low dimensional space. And unfortunately, this movie's broken, but so I can only show the first step of training, which is this right here. But you can see how this is giving a piecewise linear approximation of this manifold. And basically, if I was able to run this, you would see this running all the way down to 10 to the minus 4. Oh, actually, wait, did it just run? Oh, it is running. Anyway, there it is. So another Tori example along these lines is showing how this can break the curse of dimensionality very explicitly now, right? So imagine that you have a d-dimensional hypercube, a unit hypercube. And so you're going to define a manifold, which is a 1D manifold. It's just a line that goes from one corner of that high dimensional box to the caddy corner, to the opposite corner of the box, right? Described through this parameterization in terms of T. And so we can define a function in this case, normalized appropriately by D so that you don't get funny scaling as you go to higher dimensions. And so what you can see with this is that with this autoencoder setup, right, it doesn't matter if you're in 1 dimension, 10, 100, 1,000 dimensions, you're able to regress this latent low dimensional manifold to 10 to the minus 5 error independent, and it converges independent of what your ambient dimension is, right? And so I don't have results ready to show yet, but this directly maps onto to UQ and things like that. So now I'm going to shift gears. I'm going to talk about mimetic methods, physics compatibility, stability, and so on. And so the viewpoint for this is we're going to think about control volumes and integral analysis. So, you know, an undergraduate, graduate, most models now are steered by differential analysis, but there are historical reasons for this. It's because in the 1800s, there were no computers. People had to do things analytically with pencil and paper, like Fourier, right? And there's a very good reason for doing physical models in terms of PDEs. But an alternative way to do modeling is in terms of integral balances. And some people like to make the argument that this is somehow more fundamental, right? That this is only, if you're doing a simulation based off of PDEs, it's only convergent to your actual model as your mesh goes to 0, for example. And also maybe conservation structure and so on. That depends on your resolution, depending on how you set it up, right? Versus if you do integral analysis, then it preserves desirable structure no matter what. It doesn't matter how coarse you set things up. And so, for example, if any of you have an undergraduate engineering background, the way we're taught these kind of things is in terms of control volumes. And really, you can view this as like a single element, right? You're able to characterize many systems actually pretty well, just in terms of these kind of integral balances. And so the idea is that we're going to use graphs to model these control volume analyses. So for each cell, you'll have a node. For each face, you'll have an edge, for example. And this kind of analogy ties to, in the early 1900s, there's a lot of work with circuit analogies for mechanical and thermal systems that are still commonplace today. So many electrical engineers still use these kind of things. And these are actually, you know, if you're into this sort of thing, in the early 1900s, these models were the roots of algebraic geometry and also early finite element methods. So, you know, today this has evolved to what's been called physics compatible discretizations for PDEs. And the idea behind these, it's a broad class of methods, but the idea is that you use generalized Stokes theorems to approximate your vector calculus operators, like your div, grad, and curl. And so by doing that, you preserve certain topological structure in the governing equations. And by doing that, you mimic properties of the continuum operators, right? So things like conservation, involution conditions for electromagnetism, maximum principles, things like that. And so these will often be called mimetic discretizations as well, because they mimic those properties. And so if you're unfamiliar with these, it's a little bit of heavy machinery. So it's probably beyond the scope of this talk, but I'd like to just give the flavor of it, and so that you have a feel for how we're mapping this into the machine learning world. So for these methods, broadly, in broad strokes, you have two ingredients. One's a topological structure. So typically that would be a mesh. That'd be cells, faces, edges, and nodes in R3, each connected by a boundary operator. And this boundary operator, for example, the thing that maps a cell to the faces on its boundary, has the property that the boundary operator squared, right? If you take the boundary of a boundary, is equal to 0 no matter what. And that has some deep connections to algebraic topology. And so for us, we're not going to work with a mesh, we're going to work with a graph, right? So you can think about k-cliques, which are ordered k tuples of nodes. For example, a node is one clique, an edge is a 2-clique, a cycle of 3 nodes, like a loop, would be a 3-clique, and so on. We're going to use this graph as an inexpensive surrogate for this topological structure. Right? And then the second piece is metric information. So typically, at least for low order mimetic discretizations, this would be measures associated with mesh entities, right? So it would be cell volumes, face areas, edge lengths, and so on. And it's this metric information which gives you vector calculus operations that converge to the differential ones, right? So for example, if any of you have done finite volume methods, right, this is how you would approximate a divergence. And there's two pieces, right? The first piece on the right, everything, the sum and everything over here is just, you're just summing up a bunch of flexes, right? You're just gathering these things up, and this is purely something about what faces are attached to what cells, right? So this is ingredient 1. This piece is ingredient 2, right? You have to divide by the cell volume in order to get something that actually converges to the vector calculus. So the issue is that graphs are purely topological, and they don't have any of this metric information. And the idea behind all of this stuff is that we're going to use machine learning to extract this missing piece from data. Okay, this slide and the next one are probably very heavy if you haven't seen this stuff before, so I'm just trying to give a high-level picture. But the way this stuff all gets stitched together is you have what's called a chain complex. These are sets, and for example, sets of cells, sets of faces, sets of edges, sets of nodes with the boundary operator that I mentioned before. Then if you go to the generalized Stokes theorem, right, you have your chains, right, the things that sit in the sets of the chain complex, and you have these boundary operators. And so if you have all of these things, it induces a derivative operator here. So this is called a co-boundary operator, but what you should think of is the Gauss divergence finite volume operator I had previously, right? Once you have all of your faces, right, and you know what cells they connect to, that induces a divergence operator in that example, right? So you call this a cochain complex, right, which is now how, for example, face fluxes combine to approximate a divergence on cells, for example, right? And so in R3, this would be the div, grad, and curl. And this has the property that you inherit this exact sequence property. So the boundary of the boundary being equal to 0 translates into the divergence of the curl is equal to 0 and the curl of the gradient is equal to 0. And then the final ingredient for these things is what's called codifferentials. And the idea is you choose that this is where the engineering or the design part of building a numerical method comes in. You choose a inner product in order to induce what's called a codifferential, right? And so this is as simple as if you think back to like nodal Lagrange finite elements, right? This is as simple as you start with a gradient operator, right? Like grad v, the integral of grad v dot u, and then you integrate by parts. That would correspond to choosing an L2 inner product. You integrate by parts, and then that would induce a divergence operator, right? So that's how you get these things. And so now you have these chains of of operations. And so this is where this step right here is where the data comes in, right? We're going to machine learn. Specifically, what we're doing is we're going to machine learn this inner product space. So for this inner product, we're going to parameterize it like so. These are finite dimensional sets, so you can write it in terms of this quadratic form. And so for this matrix, we're going to assume it's a diagonal matrix with positive learnable entries. And so this gives you this big commuting diagram. And the way to read this thing, it's a little bit of, there's a lot going on, but along the center, you have your graph calculus, right? So you have like a graph gradient, a graph curl, a graph divergence, and so on. And this has the property, right? Like graph curl of graph gradient is equal to 0. You can build up a graph Laplacian as the graph divergence of the graph gradient and so on, right? But now what this lets us do is this data-driven metric information lets us bootstrap this exact sequence, right? So now, for example, say you have your graph gradient right here. Now we have a data-driven operator that has a data-driven gradient, which preserves this commuting diagram. And basically what that means, right, is that we've bootstrapped or we've upgraded the exact sequence property of the graph calculus, right? So the graph calculus, right, if you go from here to here and here to here, right, this corresponds to taking the curl of a gradient and now which is equal to 0. And now due to the commuting diagram property, right, you have a trainable object, like a learnable object that preserves that structure. Okay, so all of this, if you're not familiar with this, this might seem like, what the hell is this all about? This seems, maybe like self-indulgent. It's just a bunch of like fancy math, but it's actually super, super concrete and very practical. So what this gives you is a way of learning differential operators, which are locally and globally conservative, because it's tied to this, these co-boundary operators, but it's tied to the generalized Stokes theorem at the end of the day. If you build Hodge Laplacians, right? So this would be like a graph Laplacian, or in this case, an updated graph Laplacian, or higher order Hodge Laplacians. So these are the kind of things that come up in electromagnetism. These objects are guaranteed to be invertible. They have a well-characterized, well, they're guaranteed to be invertible modulo a null space, which you can write down with pencil and paper. So you can actually solve these things. They're positive definite, and you have all of the things you need to analyze them. So you have like Poincare constants and things like that. So you can actually, you've got some building blocks that you can use to start doing numerical analysis. And a more subtle thing is that this gives you a Hodge decomposition, and you might be familiar with this from undergraduate electromagnetism, or wherever you might have seen it, that a vector can be decomposed. The version you might have learned back then is that a vector field can be decomposed into the gradient of a scalar potential plus a curl of a vector potential. And this holds across this whole, what people call this a de Rham complex. And so this allows you to treat the non-trivial null spaces that are particularly challenging for electromagnetism. And so, for example, I don't want to be too trite because there's a lot of depth to this, right? But it gets back to this question in topology about whether something's diffeomorphic to a ball or to a donut or so on, right? So the null spaces in electromagnetism are tied to what the Betty number, which is the number of holes, right? So for example, these donuts, right, have a non-trivial Betty number. And so the null spaces for the actual matrices, if you want to do Maxwell's equations, you have to be able to factor these in. Otherwise, you'll just get like the spectrum completely wrong and all sorts of things like that. So it's a bit subtle, but this gives you all the building blocks you need for that. And so if you're interested in the details, you can take a look at this paper. There's all this analysis and stuff like that I'm not going to discuss. Okay, so how would you actually use this in real life? So say you wanted to build a surrogate for the Darcy equations. This is the idea. You take your high fidelity solution, you partition it up. In this cartoon, I'm just doing METIS, a graph cut algorithm. You can do much more sophisticated things. But once you have a partition of space, now you have your chain complex. You have a set of nodes and edges. It's your model backbone, and you'd like to hang a model on top of it. And so what you do is you reach for the corresponding things, right? So here's a divergence. I'm going to take this data-driven graph divergence now, and I'm going to take it. It's going to map all of the edges back to nodes, right? This is what a graph divergence looks like, okay? And this is conservative. So this preserves all the conservation structure in the sense that, you know, this edge contributes to this node, equal and opposite to what gets contributed to that node. Okay, so that's conservation of mass in this example. You're not allowed to mess with that, right? But fluxes are actually more empirical, right? So the way we're going to handle fluxes is, again, you reach, you know, you have a gradient here. So you reach for your data-driven gradient operator. And then together, right, if you take the divergence of this gradient, this gives you a graph Laplacian, right? But we add this black box neural network flex. And so basically what that means is we can learn from the data any model really that can be written in terms of this conservation law form. And we're expressing it as a perturbation of a diffusion problem, right? And the game that we're trying to play is like what people always do with artificial viscosity in numerics, right? This provides a means of stabilization so that you can try and prove things about this, right? So in the full-blown setting, right, on the general de Rham complex, this is what it always looks like. It's the same picture, right? You have some conservation law, right? It'll be conservation of fluxes or circulations or whatever, depending on where you're looking on the de Rham complex. But your fluxes you're going to write in terms of a gradient flux and some perturbation by a neural network, right? So this is meant to be a general nonlinear flux with the assumption that epsilon is in an appropriate sense small. And I'll explain what that means later. So you can show that this ends up giving you, you know, regardless of it, you know, it might be helpful to go through the paper and follow the details if this isn't clear, but the punchline is that at the end of the day, you get this kind of bilinear form, right? This gradient flux combines to give you a Hodge Laplacian. And so this is an invertible, symmetric, positive, definite bilinear form. And all of that metric information, all of those parameters that were learned in that exterior calculus are embedded in this matrix, right? Then you have a nonlinear perturbation of that over here, right? And so this is a perturbation of a nice, well understood elliptic object that you can work with. And so the idea with all of this stuff is now you can set up an equality constraint optimization problem, right? You could do, you know, it's PDE constraint optimization in a sense. There are no PDEs, but graphs, but it's the same idea. You have some data. You'd like a model which is able to reproduce this data. You'd like to discover this model or this surrogate, right? And so you want to impose this as a equality constraint. And so if you can impose this as an equality constraint, then that means all of this physics holds to machine precision independent of the amount of data that you have. So you can ask, is the PDE constraint well posed? And it actually is, and this is partially why we set it up the way that we did. So this bilinear, I won't go into the details other than to just say, this bilinear form has a Poincare constant associated with it. If you assume this nonlinearity is Lipschitz, right, then you get a constant like this. And it's the usual thing, right? Like if this is sufficiently large to control the nonlinearity, then you get well-posedness and stability. And so you could actually impose that, you know, this constraint, this requirement that CP is bigger than CN during training. In practice, we don't actually even have to do that. It just naturally pops out, at least for the systems we've looked at so far. And so the way that you would train this is, you know, the usual PDE constraint optimization way. Given your current guess for the model, you solve the forward problem. You use that guess, you plug it in here to solve the adjoint problem and get these Lagrange multipliers, right? So this is a Newton solve. This is a linear system solve. And then at the end, you take a separate gradient descent to update your model parameters. So these would be the metric information in the graph calculus plus whatever weights and biases you have in the nonlinear fluxes. Okay, I have I'm kind of running a little bit slow, so I have these pictures showing how it works. I'll probably just skip to the punchlines, but basically I'm looking at a class of elliptic problems for Darcy and also for magnetostatics, where you have discontinuous material coefficients. So this is kind of one of the canonical success stories for doing discretizations with this is if you just use a normal finite element method for these, you'll get spurious oscillations, things that look like rung phenomena near material interfaces. So these are just some pictures comparing to a traditional finite volume method with the same number of partitions, and showing that we get, even with a very coarse partitioning of space, you actually match the moments of the training data exactly, right? So we're training in the PDE constraint optimization, what we're doing is we're training it so that each subdomain matches the zeroth order moments of a high fidelity solution. And it turns out that you can match them to machine precision. This is kind of a toy nonlinear problem. Basically assuming it's one of these 5-spot problems, you have a point source, point sink up here. You have an inclusion, but we're assuming that the conductivity is proportional to this potential drop, this voltage drop, right? So it's basically, it's becoming more conductive as you apply a larger load, right? And this is just showing, you know, the dashed lines are the high fidelity result, the solid lines are what this kind of surrogate pops out with this very coarse graph. Same story for magnetostatics, right? That now if you have an inclusion whose permittivity, no, I always get those mixed up. I think permittivity for magnetic fields, but the permittivity is proportional to the magnetic field that you're applying to it, right? And so you can see this is the high fidelity thing. This is the representation of it on this coarse grid. And you can see that the moments are identical, and also that you result this jump that you get in the magnetic field due to the change in material coefficients. There's no oscillations or anything like that, right? So this is nice because it's exactly divergence free, which as you go to a full-on Maxwell is super important. It gives you these sharp treatment of material interfaces, right, around here. It conserves circulation. It's guaranteed to be solvable. And now it generalizes in the sense that what we've learned is a model. We're not learning how to interpolate between data, right? So you can solve this model with whatever boundary conditions you want, and it'll generalize perfectly fine. Right, and so I kind of alluded to this at the beginning. This is what we're doing with semiconductors. I'll point to a paper at the end where if you're interested in semiconductors, you can see how it actually maps on, right? But this is the exact process that we're doing, right? So we get this graph through topological data analysis of a high fidelity solution, but then we're training on this graph exactly this PDE constraint optimization approach, right? So the surrogate that you get out, it's guaranteed to be invertible, it conserves charge, all these kind of nice things. And what that means is that now you have this submodel here, right, which can be encoded into a circuit solver. So there are things like Zeiss and Spice. And so now you've got this, you know, this little module that you can hook into everything else, but you have this, it's a robust data-driven module. So I'll end here. I just want to give acknowledgements to all the people that I work with, in particular Xiaojia Hu at at Tufts University in Boston or Medford, who's done a lot of the work on the exterior calculus with me. And so today, basically, I just talked about the some toy problems, pedagogical examples, and so on. We have a ton of actual applications work related to this. So for subsurface flow, magnetohydrodynamics, semiconductors, which I mentioned a little bit, fluid mechanics, solid mechanics. And so we have tons of projects, and it's very difficult to find people who know scientific computing and machine learning. So we're very aggressively trying to find postdocs, collaborations, and so on. So if that's of interest, please feel free to send me an email. And I'll just leave this up here and then hopefully take some questions if people have any.
Thank you, Ed. It's very interesting. Are there any questions from people in the audience? Just raise your hand or unmute. If not, in the meantime, you mentioned that this type of work helps to stabilize when you couple these machine learning models inside a larger coupled model. Mm-hmm. What part of it is actually responsible for the stability?
Sure, yeah. So this is, I mean, I want to pull up a good picture. Right, so a way that you can think about this is that this is learning a Dirichlet to Neumann map, right? You're learning for a given, maybe this is the one to have up. You're learning this bilinear form, but it has boundary conditions set into it, right? So you're training this so it learns how, for example, if you apply a certain Neumann condition, you're telling it how this domain responds to that Neumann condition. So there's a ton of methods in the numerical PDE world, which are designed to couple through that. So there are things like mortar methods and multi-scale mortar methods, which are kind of based off of that idea. Hybridizable DG has the same kind of idea, right? And so the idea is if you have different subdomains, I'll just draw a little picture, right? If you have little subdomains, right? And you parameterize their trace space in between, right? All this subdomain needs to know is how it responds to this trace space. So to globally couple everything together, you just need like a finite element space for this, for these interface conditions, right? And then you'll have this data-driven thing that can explain what's happening locally in response to those fluxes. And so the key thing for making all of this work is that you're working with the appropriate differential forms. So the fact that we're working with, you know, in the case of Darcy, for example, right, we're representing things in terms of fluxes, that directly translates to a mathematically appropriate interface condition for matching this trace space. So that's the idea, right? But basically all of this analysis, it's kind of plug and play with existing things from hybridizable methods.
Okay. Thanks. I think Richard has a question. Go ahead.
Yeah, hi. Thanks for the nice presentation. Can you hear me okay? Actually, it's been a while since I've used this. Okay. I'm wondering to what extent the whole, you know, de Rham complex, the mimetic framework is strictly necessary. I mean, you're injecting a neural network into your solver at some point underneath the conservation law. So could you not do the same thing with a standard finite volume method? You modify your flux with a neural network, and you also then have conservation of mass and momentum potentially.
Well, I would argue you don't need this, right? This is just a choice about how to set these things up. There are desirable things, right? Which is that you can start proving things. Even with standard finite volumes, it's difficult. Forget about machine learning, right? It's not natural. It's difficult to talk about stability, right? And part of the whole exterior calculus stuff is that you get things like the discrete exterior calculus, which is a staggered finite volume scheme, right? So in a certain sense, the finite volume, if you wanted to just do the finite volume method, that would be this one leg of the DRAM complex. That said, if all you care about is, you know, in terms of this machinery, it's really just like a choice of notation in a certain level, right? If you wanted to just go into your code, use a finite volume operator for your divergence, for a discrete divergence, and say your flux is equal to, you know, is equal to some neural network of the pressure in each adjacent cell, that would give you the same thing as this. Like this would give you the same matrices and things, right? So I think in a certain sense, you know, you can choose to do this with all this notation and stuff. It might be simpler to just, like you say, just go for a finite volume method.
Right. But you have lots of nice machinery and you want to use it. I understand that completely.
Yeah.
When you're constructing this neural network flux on this slide, this is a function of the local state of the problem, or it's a global function of global state?
If you want it to be, if you want to be able to prove that it's well post, this would be a neural network, right? So let's say we're looking at this node and this edge. The neural network has to be a function of the difference of these two nodes. Right, that's the condition for the analysis to work. We use it all the time where the input to the neural network is, it's two-dimensional. It's the state at this node and the state at this node. In principle, it could be at all of the nodes if you wanted. Right, if you were thinking about some sort of like non-local operator, if you're...
Yeah, I was thinking of maybe including some non-local physics that isn't present in your,
so if you work with a graph, you know, this might be getting too much into the weeds, right? But the non-local calculus, if you discretize it with a 1-point quadrature rule, you actually get the graph calculus. So if you choose, so it kind of comes down to the choice of a graph. If you have a fully connected graph now, right, not just nodes connected to neighbors, right, but every node's connected to every other node, then you can actually learn the graph calculus, and the neural network doesn't have to do anything, right? This can actually just exactly recover that. But right, those are some choices about how you'd want to set it up. What's attractive about that is now the non-local diffusion is lumped into this Hodge-Laplacian thing, so you can prove more. But you could also lump it into the neural network if you wanted.
Thanks very much.
Yep.
All right, Benjamin, you want to ask something? You're still muted, I think.
Sorry. Yeah, I was wondering about, in a sense, you also said it's a multi-scale problem that you want to solve, right? There's some coarse scale behavior that you want to capture with the neural network. And did you look at what, for example, in this case, this n sub eta phi is looking like? Does it give you a physical interpretation? And the sort of related question is, if you try to solve these type of multi-scale problems, essentially you're solving inverse problems, right? You try to say something about the small scales, and you only have the large scales. So is the neural network somehow providing that regularization for you in order to get that?
Right. So to make it concrete, some of the multi-scale problems that we're interested in, I'm just going to sketch a cartoon here, right? Is we have a lot of like additively manufactured materials that we're interested in at Sandia, and we actually have pretty sophisticated imaging for these things. So basically at like a sub-micron level, you get a sense of exactly the microstructure and what it looks like and so on. And the lab has also invested in automatic meshers. So it will go through this entire thing and build a TET mesh for it so that you can solve, you can just solve the forward problem on this thing. Of course, that's absurdly expensive. It's like, but the idea is now what we can do is we can break this into elements, right? And now each element we can use these automated meshers. to figure out exactly what should be going on, right? And so this model, this surrogate that we're solving here tells you exactly at the microstructural level. So if you're familiar with multi-scale stuff, there are things like finite element squared and homogenization, and there's all these different tricks. But oftentimes they have to make an assumption about, like, you have a periodic microstructure or whatever. So the idea with this is your training data can actually be the fully resolved actual experimental microstructure, and you're training your neural network to represent at least a coarsened version of that microstructure. And it's particularly important for example, for flow through porous media, you'll have transport channels, right? So you might have something which is very conductive, but just along this very narrow band here, right? And so if you do homogenization of this entire thing, you can actually get flow that goes from here to here, right? When in reality, flow is only allowed to traverse this kind of highway. So basically what you're learning is in this Dirichlet Neumann map, right? It is a homogenization that when you solve it, it will give you this kind of coarsened version of what's actually happening at the microstructure. We probably have something coming out about this in a few months. So if that's something you're interested in, you know, at this point, it's kind of hand wavy, but
I understand what you say, but I don't fully understand that the neural network takes as input phi, which is basically, okay, the flux of your core scale model, right?
So phi, in this case, phi would be a pressure. F would be the fluxes, the velocity field.
Yeah, sure. Okay, the gradient of phi, I mean, but it gives you some core scale pressure or fluxes. So if you so you try to say something about the, let's say, the high fidelity stuff, while you only have the core scale solution, right? That's what you have learned with your neural network, effectively.
What the neural network tells you is a model, right? So usually, like, how would you do the finite volume method? You would discretize these flux equations, right? And the PDE would tell you what fluxes to evaluate at the interfaces, right? What this model gives us instead is that the neural network tells you what the flux function is, right? For example, as a function of these two state variables, it tells you what flux will go through it. And you're parameterizing that by saying, you want to reproduce at the end of the day a set of pressures that is consistent with a high fidelity solution, right? So in this kind of cartoon, what that means is that you'll have a pressure gradient along this channel. You'll have a constant pressure over here, constant pressure over here, right? Does that kind of make sense?
Yeah, I see your point, but again, I think maybe I cannot phrase the question well enough. So let's see if other,
maybe
other people have questions. Yeah, sure. Maybe I can ask something else about, you were talking about legacy codes in the beginning and getting stability and so. But if you do this type of methods and you need to get gradients, I don't know exactly how you train the network, but I think you need to, you sort of need to have your neural network embedded in your solver and be able to get out all the gradient information as well, maybe. How would you do that in existing codes?
So to train one of these models, right, you just need to use your legacy code and say, for these boundary conditions, this is the response, right? So for example, for this one, right, these are the flux conditions at the boundaries. It generates this field. This is a black box thing. It's not intrusive to do that, right? Then you need to do some post-processing. You need to like do this coarsening and so on. But this is totally, this is non-intrusive, this whole process of extracting a model. Then, and this is common for many of the DOE codes, because we have so many legacy codes, we couple through interface conditions. So there's kind of handshakes at the boundaries. So for example, to be concrete, the atmosphere and the ocean have a shear boundary condition between the two of them, right? They're coupled together. And so the way these kind of production codes work is that they will they'll do this kind of mortar method approach, and so you never actually have to push. The two codes never actually have to reach into each other's guts, right? They just have to be able to assemble their own piece of the problem and then communicate through boundary conditions. So there's no, in order to do this whole process, right? You don't need to do automatic differentiation or anything like that, right? It's just you need to know how to respond appropriately through the Dirichlet-Neumann map. Of course, a lot of the codes we do have piping with automatic differentiation and so on through many of these. So it's available, but it's not necessary.
Right.
All right. I dropped out for a second, but are there any other questions, perhaps?
I have a question. Thanks for the interesting talk. I have a question about the first sort of theme that you showed. So you mentioned that you can sort of identify structure, for example, with an autoencoder, a low-dimensional manifold in a high-dimensional data set. But what if there is some kind of ambiguity? For example, if there are two circles, if there is a line and a circle, for example, what happened? What do you think happens in that case? Will the method still work?
Oh, I don't know. I mean, I would expect it wouldn't work as well, for sure. I mean, there are certain, and this is working with autoencoders at all, right? Forgetting about the partition of unity stuff. For example, if your data lives on a two-dimensional manifold, but you have width 1 at the center of the hourglass for the autoencoder, right? Then what it will do is it will do a space filling curve if you do these kind of experiments. So they'll always try and do its best, right? Like, but there is a certain architecture calibration that comes in, right? So an autoencoder on its own, if you had a non-trivial topology if you didn't have a simply connected manifold, it would probably try and figure out how, might try and come up with coordinates that go from here and then over to here. Like it'll do its best, right? But it can't on its own figure out how to handle that optimally. So that is, but the kind of things that we've been looking at are, basically you have things that are diffeomorphic to a hyperplane, right? So in chemistry, turbulence and things like that, you just kind of have these high dimensional surrogate spaces, but they just look like topologically, they just look like a plane. Works well for that, but that's about all I can say specifically.
All right, thank you.
All right, anybody want to ask something to Nat? If not, I think we can close. Thank you very much for getting to talk with us so early in the morning.
Yeah, no problem. And definitely please feel free to reach out with email if you're interested.
Yes, thanks. Thank you, everybody, and see you at the next meeting.
Yeah, thanks very much. Thanks, Nat.
Richard.
Yeah, I feel like there's something I don't quite understand about what he was doing. It's definitely something interesting, and
I guess your question was pretty good. Hey, are you father of a second child?
yeah, I am. Yeah.
Oh, congratulations, man.
Guess what his name is?
Benjamin.
Exactly. Yeah.
Is it true?
It's true.
It's not. It's not true.
No, it's true. No, we have one of my grandfathers was a Ben, and we were looking for a name that's kind of Dutch and works well in Dutch and works well in English and it's a bit simple, and yeah, that was
Wow.
what we came up with.
Good job. But it's a crazy time, no? How are things?
Fine. Since the Kramsorg took up a lot of space in the house, let's put it like that. But now she's gone, things are kind of settling down a bit. So yeah.
Okay.
Annette's parents are here, so they're also taking care of it. And the way we've divided it up, I'm more or less taking care of Emmy, and Annette is taking care of Ben. So yeah, for like 80% or something. So that seems to be working okay so far. Let's see how it goes.
Wow. It's such a special time with super little ones.
Yeah. The best thing
are you catching some sleep or?
Yeah, no, he sleeps super well, and yeah. So, and I cancelled like all my meetings for 2 weeks, so I have lots of time to do fun stuff at work. So I'm actually quite enjoying
excellent.
some.
So it's 2 weeks ago now.
Yeah, when was he born? He was born on 15th. So okay. Yeah, getting on for 2 weeks.
Yeah, exactly 2 weeks.
Yeah. And how are you doing?
But you will take some more leave, I guess, for the coming time.
Yeah, definitely this summer I'm going to take a lot of leave because I'm quite tired of everything. So if we can go somewhere, that's a bonus. But if not, then I'll just take leave and stay at home.
Yeah, sure.
Did you meet Gustav today, actually?
Yeah, I did. Yeah, things are okay. He has progress. I think he's really wrapping up. That's good. He did one other test case, another Taylor green vortex, but the results don't look so good. So maybe he should not include it.
It's very late to look at another case.
Yeah, it's late. It's true, and I think the test case was too complicated. It was, he should have taken it from like it was in the literature, but apparently it was not like that in my code setup. So anyway, and then it's more difficult to see if the things that come out make sense, right?
Yeah.
Anyway, I think there's only one thing maybe for you that you could get involved in, let's say in 2 weeks. I don't think you need to attend the meeting, but I think he is going to plan, or he wants to plan committee and defense date and graduation province. So that there's probably one administrative thing that you should do.
No. I mean, I'll be attending the meetings as soon as I'm back normally. But I mean, is there a meeting next week already?
So I'm taking some holiday next week. And the week after, the normal meeting is on Thursday, and then it's Ascension Day. So we have planned a meeting on May 11th instead, on Tuesday.
Okay. What time is that?
At 11.
Yeah, okay. Then I'll go to that one.
All right.
Yeah, but the next step is basically having a draft thesis, right? The next step is the green light meeting. And for that, he needs to show us a mostly complete thesis.
Oh yeah, I see. Okay.
So I'm not sure how close he is, but we can discuss that anyway.
Yeah. Last time he said, I want to graduate in six weeks from now. I think that was 2 weeks ago. So I said, okay, it's a bit optimistic.
Yeah, no, okay. I'll be alone.
He didn't really he didn't realize that it takes like 2 weeks for us to read, and then he has to make changes also, right, depending on what we say, and then it has to be submitted a couple of weeks, maybe 2 weeks in time to the committee.
Yeah.
So,
no, it's even worse. There's like a month from the green light, from when we say that the draft is acceptable until the defense. That's the minimum amount of time. So yeah, he has to do other stuff in the meantime, prepare his presentation, apply for jobs and things.
Yeah. Okay. Well, good. Hey, all the best at home. Congratulations to your wife.
Yeah. Thanks. Yeah, I'll let her know. Is this now the replacement for Crux? Is Crux is no more?
Yes.
Yeah, it's a lot better.
Yeah, we stopped. Yeah, Wouter has been advertising it broadly, so it's not just for our group, but yeah, it's also the Amsterdam Data Science or whatever it's called. There's a mailing list, and there's some other groups that he involves in the mailing list. So indeed, there are more people coming. And the focus is not just UQ, but it's machine learning, UQ, PDEs, a bit like that. So, and Wouter is pulling it. I did a couple of years, and now Wouter has the chance to do it. So, yeah, that's about it. All right, I need to go and make some food. My son is just arriving home.
Yeah, I got to check on some stuff as well. Okay.
Okay.
Anyway, it was nice to chat. See you in a couple of weeks.
Indeed,
Have a good holiday.
yes. Thank you. See you.
Bye.